His work on cryptography has, like, okay, to be completely fair, I don't really understand cryptography, which is part of the reason I'm here. But you know, the handful of papers I've tried to read and the very, very interesting application spaces that it's been a part of, I think, are hugely relevant now more than ever. I wonder why. But yeah, let's give it up for Josh, and we'll see you guys at the end.
Thank you. So, first question is, am I projecting well enough?
Or do I need this? Should I use this?
You need this.
Okay, let me.
Try this fancy trick. Does that work? That seems to work. I've never worn one like this before, but as long as it works, I'm happy. Thank you, Kabir. Thank you to all the organizers here. This is my first time in Urbana. I'm a little bit embarrassed to admit I've really enjoyed my visit thus far, except for one thing. It is still summer, but this is crazy. Too much for me. Anyway. I've been working on election technologies and various, but by the way, I see a couple free seats here, one there.
If there are any other free seats around, please sort of help your neighbors by identifying. Okay. A few there, so feel free to grab them. Or if you like to stand, that's fine by me. So yes, I've been working on election technology for literally over 30 years, back to my doctoral dissertation. Mostly writing papers and such, and suddenly, for some reason that I can't quite figure out, people seem to care about this all of a sudden. So I'm not quite sure what's going on, but let me start with one of the things that's going on, since this is hot off the press. Literally 2 weeks ago, the National Academy of Sciences came out with this report on securing the vote, making a lot of recommendations, findings, and such on what election technology and systems should look like in the future. There are still a few more seats around if people want to try to grab them. Since it's so new, I just want to start here, give a little bit of a sense of the highlights of the report, and talk about what's going on, and then we'll take a deeper dive into some of the aspects that I'm personally most interested in, although everything here is quite reasonable. So to begin with, the report did get a good deal of press, even in an environment where getting press is kind of hard these days because there seem to be other things going on that are sort of sucking up all the oxygen. But there were 2 articles in the New York Times. This is, the one on the left is just the AP story. But the New York Times' own article, the USA Today had an article, Nature, The Hill and Politico both had features on this. So what did we say? Because that's really the most important thing here. First of all, one of the findings was that there was clearly significant Russian intrusion into the 2016 election. Most of what we saw was in the form of disinformation. There's a lot of that. We know a lot of that. There were some intrusions into voter registration databases. But one important thing to mention is that there's no evidence of actual tampering with the votes themselves. It doesn't mean it didn't happen, and doesn't mean it's not possible. It's just we haven't seen any evidence of this. I was on a call with election officials from all over the country 2 days after the 2016 election, and the consensus was that as far as casting and counting of votes go, this was the cleanest election that anybody had seen in a long time. That said, we know that the system is extremely vulnerable. Just because we didn't see evidence of it happening doesn't mean it can't happen. In particular, I like to use this quote from Alex Halderman at the University of Michigan. I've worked with him a lot. He has said that his undergraduate security class could have changed the results of the 2016 election. And I believe him. He was involved in the Michigan recounts in particular, but some of the other recounts that took place after 2016. And some of the vulnerabilities that he discovered were just jaw-dropping. Places where a very small number of people could have changed huge numbers of votes quite easily with very little skill and expertise. And I'd be happy to talk more about some of these things later on, but I don't want to delve into that now. But there's enough here to be really scary. So one thing that's clear is we need to apply the best practices that we can. We're usually called best practices technically, the sorts of things that industry typically uses, the banking industry, other critical infrastructure environments use to protect both our registration databases and the voting systems. But it's also important to recognize that best practices, in some sense, the best we could normally be expected to do, just aren't enough here. And the problem is that this is an asymmetric battle. Elections in the US are typically run at the county level. Most states, it's counties. There are just a couple of states that do things statewide. In much of New England and the far eastern states, it's actually done at the municipal level. Townships run their own elections. So there are over 8,000 election jurisdictions in the US. And do we really believe that some small county in Illinois or the state of Washington or many other states can really effectively stand up to a concerted attack from the Russian FSB or APT-1 in Shanghai or North Korea or Iran or any other nation-state level attack against a little county government that's got maybe an IT administrator that's trying to keep a firewall up to date and installing patches now and then? So it's not a fair fight. And we really should accept that the situation we're in is that there can be penetration, and although we should do what we can to try to make it harder, we can't expect to prevent all attacks. But there are things we can do nevertheless. So I'm done scaring you. Now I'll try to talk about some things that we can do to help. And in particular, since we can't ensure that the systems cannot be attacked, we can still audit them and at least know if there has been an attack and then take action. And the thing about voting that's so different from other fields is, for instance, in banking, if you're double charged for something and your bank account is deducted someplace where it shouldn't have been, you can tell. You can see that. Hopefully you can get it fixed. Maybe you've got some records, whatnot, but at least you can tell. If you order something online and the wrong thing comes, again, you see, oh, something is wrong here. You can complain. You can hopefully get it exchanged. You can get it fixed. And in just about every area of discourse, if something that you intend to happen doesn't happen the way you intend it to happen, then at least you're aware of it. Sometimes it's hard to get fixed, but at least you know. But in voting, you cast a ballot. If it gets changed somewhere along the way we do things today, you don't know about it, right? Thousands of votes could just be flipped. And, well, okay, I think I voted this way. How is it counted? I don't know. So it's actually really hard, but not impossible, to make it so that you can actually check and make sure that your vote has been properly counted without compromising the privacy that we've come to expect and should expect. So auditing is really part of how this is done. And there are a couple of different types of auditing that are commonly used, or maybe not as common as I would like, but we talk about in the report being used. So the first is an administrative audit called a risk limiting audit. So you can imagine what you think auditing is in an election. Well, after the election, you pick some random sample of the precincts or the ballots cast or something, and you do a recount there, and you make sure that sort of is consistent with what you expect, and that confirms things. That's been done for years. Some states, some counties, some jurisdictions do it much better than others. But so we have some familiarity with the process of pick a random precinct, count up the votes in that precinct, make sure it matches what you're expected to find in that precinct. Do that for 1% of the precincts, 2% of the precincts, and maybe you get some confidence. A risk-limiting audit is a fairly new statistical mechanism which uses some pretty sophisticated statistics to make the sort of traditional audit much more efficient, much more efficient. So instead of having to recount tens of thousands of votes to get confidence in a large election, you can sometimes do it with only 100 votes. And there are a few tricks involved, but one of them is that it's dynamic, that in a close election, to have confidence in the outcome, you really have to look at more ballots than in an election that's a landslide. So a landslide, the result is 70-30. You count 100 ballots, those came out 68-32 or 71-29 or something like that. Okay, that's pretty good confirmation right there, especially if those 100 ballots are randomly picked. So the big trick that makes risk-limiting audits really efficient is not checking precincts, but checking ballots, one ballot at a time. You can say, okay, ballot 69384 was supposed to look like this. Does it? Yes. And if you check individual random ballots, you can do things very efficiently. It's not the only way to do risk-limiting audits, but it's usually the best. The other trick is what's known as a public audit. And it uses a technique called end-to-end verifiability. And a public audit is something very different from what you might think of, what you might be used to. In a public audit, you as a voter can check directly that your vote has been counted properly. In fact, you can check that everybody's vote has been counted properly. Just as a voter or an observer, you don't have to depend on the election administrators to do a recount or an audit or a sample. You can effectively do it yourself. You can effectively do your own recount, again, without compromising privacy is the trick. So we've talked a little bit about risk-limiting audits. They use statistics, make things better. I'm going to spend pretty much the rest of my time here talking about the thing that I really love to do and promote, and this is the end-to-end verifiability. And end-to-end verifiability uses cryptography, mostly. There are some ways in which it might be able to be done without cryptography, but the techniques usually use cryptography to enable this kind of public audit that I've been talking about, and really change the paradigm, shift the process of not we vote by giving our votes to election administrators and walking away and hoping they do things right. We vote by doing something that's part of the voting process, and we can stay involved and check as much or as little as we want to gain as much confidence as we want in the accuracy of the process. Okay, so what can we do with this technology? Turns out quite a lot. This end-to-end verifiability allows you to detect any inaccuracies, any tampering in an election. Not just, I know of this kind of attack and I've guarded against it. Any kind of attack, even things that nobody has dreamed of today. And the detection is not just election officials detecting something, it's anybody can detect something. A candidate can detect if anything's gone wrong, voters, observers, news media, anybody can check. And the things that could go wrong, I'm not just limiting to external attacks. Things that could go wrong can include internal attacks, election officials being corrupt, equipment being malicious, or the equipment vendors trying to plant something or doing something wrong. Any kind of attack. This sounds great, right? We can do a great deal. This set of technologies that achieve this, again, called end-to-end verifiability, and I need to give a definition before I start to talk about ways in which it can be done. So, we define an election to be end-to-end verifiable if two things are achieved. First of all, voters can verify that their own choices, their own selections, have been accurately recorded. And anybody can verify that the recorded votes have been accurately counted, accurately tallied. Okay? And this is, in some sense, the best you can hope to do. Because the thing that's missing is I as a voter can't tell that you as a voter have had your vote correctly recorded, because I'm, as a voter, shouldn't know what your intentions are. I can't really know your intentions. Maybe you tell me your intentions, but I don't know if they're your real intentions. Maybe you're confused and you meant to vote one way and you did another or whatnot. Effectively, you as a voter, you're responsible for your own vote, in the sense of checking that it got recorded properly. But anybody can look at all the recorded votes and make sure that they together have been properly counted. So the thing that makes elections so hard is that privacy is beyond privacy in normal means. You normally think of your bank account as private, that I shouldn't be able to tell what's in your bank account. But you could tell me what's in your bank account. You could show me a statement. You could reveal your bank account. You can reveal your password. You can reveal your credentials. You can reveal all sorts of private things about yourself. But in an election, there's a higher standard. You should not be able to prove to anybody else how you voted. You can claim to have voted some way, but your actual vote should be private and non-disclosable, even if you want to disclose it. Because if it is disclosable, then you could sell it. Or you could be coerced by somebody else who might have some power over you to vote in a certain way, even if you don't want to. But when we vote in a poll site, the usual public form of voting that we use in this country today, not everywhere, but most places, you can go into a poll site, you could have somebody outside of that poll site, maybe even walk in with you saying, you're going to vote like this, right? You're going to vote for candidate X. And you go in and say, yeah, I'm voting for candidate X, I promise, I promise. You go over, you mark your ballot for candidate Y. You drop it in the ballot box and you come out and say, yep, I voted for candidate X. I did exactly what I was supposed to. It's all good, right? Well, that sort of privacy is critical to voting, and it's a higher standard than other places. Now that I've said that, I want to point out that if we didn't have that standard, if we had open voting without a secret ballot, all the things I've talked about would be really, really easy. And that kind of open voting used to be common in the US. This is what elections used to look like. Most American presidents were elected without the benefit of the secret ballot. The secret ballot is a relatively new innovation, and it's actually something of a technical innovation. The idea of voting in private within a public environment that is monitoring and enforcing the privacy. This was a clever idea in the mid-19th century. Nobody knew how to do this before then. This is a method called the Australian ballot, by the way. It came in the mid-1850s, I think, and spread around the world slowly. In the US, if you've looked at all at presidential history, you might know that there's this little quirk that's kind of annoying, that the number of the president is different from the number of presidents. That's because Grover Cleveland was the 22nd and the 24th president, so one person was two presidents if you count differently. Well, the whole issue there, the reason for that is the secret ballot, or the lack of the secret ballot. Basically, back in 1884, Grover Cleveland was elected. 1888 was an election where Cleveland was contested by Benjamin Harrison, and that was an election that was utterly rife with vote selling, with coercion. It was just utterly scandalous. And Benjamin Harrison beat Grover Cleveland, and there was so much public outrage over the process that the secret ballot basically swept through the whole country. And by the next presidential election, 1892, there was a rematch, and with the benefit of the secret ballot, Grover Cleveland did beat Benjamin Harrison back and became president again. So that's why we have this funny counting going on. What would this look like today, though, if we had open elections? It was tricky then. You come up, you in public, state your intentions in some public forum. Today it would be a lot easier. Today it might look like a website, right? If you have an open election, then you as a voter convey your choices, your preferences, to the election office, however is convenient, right? It could be you go in and you make a statement on paper. You could do it electronically. You could do it over the internet. You could do it by passenger pigeon. It doesn't really matter. What matters in the end is there's a public accounting, a public listing that has all the voters, all of their names, all of their selections. And now anybody can look at the list and say, yep, my vote is up there correctly, and do the counting and say that the count is correct. Now, whether or not the other voters are legitimate voters is sort of out of the scope here. Voter registration databases is extremely important. Whether or not they're accurate, I'm not getting into here, but that's a public process. That's sort of easier to manage. And at least you can look, and you could check these names yourself, and you could go and see if they're real people at these addresses and such. So I'm not going to get into that. You just looking and saying, yes, these are names of people who are supposedly allowed to vote, and check them to whatever extent you want, and know that they've had an opportunity to check their votes as well. So that meets the two definitions of end-to-end verifiability, the two pieces of end-to-end verifiability. You can check that your own vote is recorded properly. You can check that all the votes have been tallied properly once they've been recorded. Okay? Easy to do. But of course, there's no privacy here. So the interesting thing, the harder thing, is how do we make an election end-to-end verifiable, have these properties, but also make it a secret ballot? And the trick is where the cryptography comes in. Add a layer of encryption, just a little bit of encryption in just the right place to make this work. So we still have this public manifest of all the voters and their votes, but the votes are encrypted. See, you can't really see what's under there, it's hidden. You see only the encryptions of the votes, and everything else is the same. Okay, so now when we have encrypted votes instead of open votes, we have to provide a few other things to achieve end-to-end verifiability. There has to be some way for Carol to check her encrypted vote and become confident somehow to be able to check and be sure that the encrypted vote next to her name really does represent her true selections. Okay? That's part one. And we have to have some way that you can take this set of encrypted ballots and confirm that those encrypted ballots correspond to the actual tally of the election. Okay? Those are the two things we have to do. And with this manifest, and that's what I'll be talking about. Is there a question back? Kabir?
If Carol can check who she voted for, can't someone with Carol's information, whatever password, whatever, by definition, also know who she voted for?
That's a great question, and for the purpose of the recording, Kabir is asking whether back here, Carol being able to check whether her vote is recorded properly allows for others to coerce Carol into voting in a certain way. And the answer is no if this is done properly. And part of the trick that I'll be getting into in a little while, I'm going to postpone that because it's very touchy, but it turns out to be not that hard, is to make it so that Carol can check and be confident that her vote is properly recorded in a way that doesn't allow her to transfer that knowledge to somebody else. So what we do is, during the time of voting, Carol can check and make sure, but once she's stopped voting, all she knows is that the vote hasn't been changed from the time that she was able to check what it was, but she has nothing that she can provide to a third party to show how she voted. And I'll show you there are actually several ways in which that can be achieved. Surprisingly, that seems like a really hard thing to do. But it turns out it doesn't even require mathematics. That's not so tricky. It's this part of turning the encrypted votes into a tally and getting the mathematical proof. There's a little bit of math in there, and I'll talk about that next. So here are the two questions that must be answered. First, how do voters turn their preferences into encrypted votes? Second, once that's done, how do we take these encrypted votes and prove that this corresponds to the announced tally? Okay, I'm going to do part 2 first, because part 2 seems like the more technologically advanced, it's more technical. If I did part 1 first, you'd say sort of, okay, that was easy. So I'm going to do something that's a little harder first, and then we'll do the easier part second. We'll do the mathematics. So we use some tricks with encryption. Most of the time, the thing you do with encrypted data is decrypt it. There's not much else to do with encrypted data. I might take it, I might encrypt it to put it someplace securely. Maybe later on I want it back, I take it, I decrypt it. Maybe I give it to somebody else, and that somebody else decrypts it. But the data it gets encrypted, moves around a little bit maybe, gets decrypted. That's about all that happens with encrypted data, usually. But it turns out it's possible to actually compute on encrypted data in encrypted form under some circumstances. So some encryption mechanisms, some ciphers allow you to actually compute directly on the encrypted data, perform some operation on 2 ciphertexts, and get a result that is meaningful and you can do something with. This is usually called, there are a few ways of referring to it, but it's usually called homomorphic encryption. If you've taken any algebra classes, not high school algebra, college level algebra, you will perhaps run into homomorphisms. These are functions that preserve structure in some form, and they can preserve the structure of the clear text just by operating on the ciphertext. So for instance, we can construct an encryption function that has the property that if capital A is an encryption of little a and capital B is an encryption of little b, then if we take the product of the 2 encryptions, what we get is something which, if we decrypt, will be a product of the plain texts. That turns out not to be so hard. But before I do that, I'll mention that we can also have encryption functions such that if we take an encryption of little a and an encryption of little b, and again, the most common thing to do is multiply the 2 encryptions together, what we get is not an encryption of a times b, but an encryption of a plus b. And that is particularly useful in the cases we'll be talking about. But let me do the multiplicative homomorphism first and just give you a sense. Let me ask, how many people in the room have seen RSA encryption? Okay, good, most, great. For those of you who haven't, don't worry about it. You could actually close your eyes for the next 3 slides. It won't really matter. But I want to show you there are some equations involved. There's actually a lot of math involved in this. But getting a sense of what's going on is pretty easy. RSA encryption really works by doing nothing more than taking a message and raising it to a fixed power, the encryption exponent e. That's all it is. Yes, you're doing it mod something. You're doing it in a ring. It's mod n. We don't have to worry about that. Really, you're just raising a message to a power. So if I take one message and encrypt it by raising it to a power, and I take a different message and I encrypt that by raising it to the same power, then what happens if I multiply them together? Well, if I take the product of these 2 RSA encryptions, then what I get, just going through the algebra, is m1 to the e times m2 to the e. Do a little bit of high school algebra here, and you get m1 times m2 to the e⁻ power, which is the encryption, or an encryption, of m1 times m2. So RSA, the very old public key cryptosystem, the very first public key cryptosystem, has this multiplicative homomorphic property. And when RSA was invented, people, you notice this, that, gee, this is interesting. I wonder if it's useful. And the answer seemed to be not very, because there aren't a lot of things that you do by multiplying things together in most common life experiences. But we can also have an additively homomorphic function. So I won't go into details of different ways of making this work, but imagine that you have a cipher where you have a fixed base instead of a fixed exponent, and the message is actually in the exponent. So you encrypt M1 by raising g to the power M1, and you encrypt M2 by raising g to the power M2. Now if you multiply these things together, do basic algebra, g to the M1 times g to the M2 is g to the M1 plus M2. That's an encryption of the sum. So we can encrypt and get a sum, and everything is good. We have an additively homomorphic function. Why do we want this? Well, multiplication doesn't happen so much in real situations, but addition comes up a lot when you're with bank accounts, you're adding dollars, subtracting dollars, moving money around, and in particular, in elections. What is an election? An election is really nothing more than addition, right? You're adding up votes. Here's the first vote, here's the second vote. You take them, you add up all the votes, and you get the tally. So really all I have to do is encrypt all of the votes, now take the product of all the encryptions, and I get an encryption of the sum. And the sum of the votes is the tally of an election. That's kind of all there is to it. Not that hard. Yeah, please.
So how would you be able to unencrypt the sum? Because theoretically you shouldn't be able to unencrypt any of the votes in the first place. So then what makes the sum unencryptable by just
Okay,
member of the
so
general public?
this is a great question. This is who can decrypt and how? And how do you make it so that you can encrypt the tally but not individual votes? I'll talk about that, I promise. Please be patient. So it's a great question, but I'm not there yet. But if I don't satisfy, raise your hand again later on. But I will talk about that specific point, but I'll give it a while. Yes, another question.
How does the mod in the encryption function not ruin the algebra that makes it multiplicatively homomorphic?
So the question is about the actual multiplication is multiplication mod n. It's modular multiplication. But everything is modular multiplication here. So it actually, you're doing all your algebra in a ring mod n. Everything is fine. And when we're looking back here, then you're adding votes, yes, in that ring, but as long as the ring that you're working in is large enough, the votes won't wrap around. So if the votes are all zeros and ones, and we'll make that the case in a moment, then as long as the modulus, or the effective modulus that you're working with, is large enough that things don't wrap, then things will be fine. Okay, that's the short answer. There might be a longer answer, but that'll say for later on after the talk. So let me just talk about the achievability of homomorphic encryption, and then we'll get back to some of these other topics. So we mentioned RSA, the original public key cryptosystem, has a multiplicative homomorphic property. But it's not the only one. Most public key functions have a lot of algebraic structure. The other most commonly used public key cryptosystem is El Gamal. Here's what El Gamal looks like. It's also multiplicatively homomorphic. Another thing that's been used a lot in theoretical work is Goldwasser-Macaulay. Goldwasser-Macaulay is an encryption function that encrypts a single bit at a time. And that bit is in an exponent. So what you get is sort of a mod 2 addition. Mod 2 addition is really just exclusive OR. So that function, which also dates back 30 plus years, has an exclusive OR homomorphic property, again by multiplying the ciphertexts. I did something, again, I'm embarrassed to admit, more than 30 years ago, which just did a simple generalization of Goldwasser-Macaulay, so there wasn't a single bit, but it was a larger value that went into the exponent. And by doing that, I could get something that's additive mod some large value, and large enough so that it covers all the possible votes. And that worked really well. I did that for election applications. Later on, about a decade later, Pascal Payet generalized the function that I did to get something that is a little bit broader with additive homomorphic properties. The issue is that my function, decryption is cumbersome, shall we say. It's a little hard. It's OK in the context of elections because you're encrypting, 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 and you just do one decryption at the end. But if you want to encrypt, decrypt, encrypt, decrypt, then cumbersome decryption isn't so good. Pascal had a way to make decryption much simpler, much cleaner, and has a lot of applications. So it's great for other things. It's a little bit harder to encrypt, but not that much harder. So they have useful properties. OK, now I'll get back to your question of who can decrypt. We don't want there to be one entity that can do decryption, because if just one entity can decrypt, then that entity can decrypt everything. I can decrypt this tally, but I can decrypt the individual votes as well. And the privacy isn't so good in that context. So we really want to somehow split the capabilities of decryption amongst some set of entities. And a convenient set, usually in elections, at least in the US, there's a body called the canvassing board. And the canvassing board usually has about 5 members, and the 5 members can decide whether or not a vote is valid. They're looking at a marked ballot. Like, that's X through, but it's X nearby. Should we count that or not? And by a majority, the canvassing board can make a decision on whether or not to count a ballot. So these are good entities, perhaps, to give decryption keys to. But not a single key. You don't want to give a single key because that gives too much power. We want to split the decryption functionality amongst multiple entities in an appropriate way. And what we typically use is not just ordinary homomorphic encryption, if that's not ordinary or strange enough, but we want to use a threshold form of homomorphic decryption so that we can create whatever threshold we want. For instance, there might be 5 canvassing board members, and 3 out of 5 are required to decrypt anything. So 3 out of 5 can decrypt the tally, but you're absolutely right. If those 3 out of 5 or some 3 out of 5 collude, they could find out your vote or my vote. And this is why we don't want to make the threshold too low. We want to set the threshold high enough so that it's not going to be likely that there'd be that kind of collusion, and especially that that kind of collusion is not clandestine. So maybe we would want to have canvassing boards be larger, make them 8 out of 10, something like that. Gives a little bit more privacy. We probably don't want to run it up to 5 out of 5 or 10 out of 10, because that means if one canvassing board member loses a key, or decide maybe that I don't lose the key, maybe I decide, oh, I can't seem to find my key. Sorry, the election's canceled. That's not so good either. So we want to add some robustness so that not all canvassing board members have to cooperate to compute a tally, but enough of them so that it would be very hard to get a collusion of canvassing board members that will get together and really be curious about how I voted and will open my ballot. Okay? So a ballot, you probably can already see where this is going, would look something like this, where maybe there are 3 contests, and this is a ballot that says, okay, this voter voted for the second choice in the first contest and the first choice in the second contest and didn't cast a vote at all in the third contest, something like that. That's kind of what a legitimate ballot would look like. And once you've got that, then it's easy to see how you take everybody's ballot, and all you have to do is add up these votes component-wise, and you get a tally of an election. And now we can use homomorphic encryption, and instead of taking the individual votes and adding them up, what we do is encrypt each of these votes, multiply them together with one of these additively homomorphic encryption functions, and decrypt just the tally so that you can see this is the correct tally without ever opening the individual votes. They stay sealed the whole time. They're never opened. They're sealed. Everything is good. Okay. So now that I've talked about this, and there's some more details I'll come back to, but given a sense of this, I want to go back and address the first question. So how do you turn your preferences into an actual encrypted vote? And this is really the question of how do people encrypt? If we were having secret ballot elections amongst computers, this would be a lot easier. But people aren't really that good at mental encryption. I'm not that good at mental encryption. In fact, I can't do it at all. So we could have voters have their own devices. You bring your own device, or you have some device that you've chosen to use. But the problem with that is if I choose my own device, it might be corrupted. It might have malware on it. Or it might be a device that was given to me by somebody who is coercing me and says, this device will make sure you vote right. Use this device. So that becomes problematic. So we really want to do things where voters use officially provided devices. They use, here's the device in a poll site. Here's what you can cast your vote on. And it's sort of been checked out and improved in various ways that's going to do the right thing, and I'll say what I mean by that, and provide privacy. The right thing in terms of encryption, we can check on. Voters can check on. But now the question is, how do the voters do the check? How do voters have any confidence that this device, they walked into a poll site, they made their selections on a touch screen, say, how do they know that that touch screen did the right encryption and didn't just say, oh, thank you very much for voting. Now the encryption happens to be encryption for something other than who you voted for. So what we need to do is find some sort of an interactive proof process. Interactive proofs come up in cryptography a lot, where we can convince a voter of something being true without giving enough information so that the voter can then turn to a third party and convince the third party. Interactive proofs usually are non-transferable, but they're also usually from computer to computer. There usually aren't humans involved. How do we get a human involved in this process of being confident that this strange set of symbols actually corresponds to the choice that the voter made? So I can give you a trick. There are actually many different ways of doing this, many clever ways that have been developed in the past 15 years or so as people have looked at ways of achieving this that are surprisingly usable, surprisingly workable. But I'll give you one trick. And sometimes I'll do this with, I'll have a deck of cards. I do have a deck of cards in my bag we could do this on, but we'll do a virtual deck of cards. And I should assure people, I have no card trick skills. So I can't do sleight of hand tricks like this. But what I'll do is, well, maybe we'll do this beforehand. Let me pick somebody in the room. Anybody want to be a volunteer? I promise not to saw anybody in half. Okay, you'll be my volunteer. You don't have to come up. You can sit there. You can volunteer from your seat. Make it easy. There are two choices, red or black. Which do you want to vote for, red or black?
Black.
Black, okay. Now I'll tell you that I would put down 5 cards, and I would tell you that they're all black. Okay? I would just make that assertion. Now, in this example, since I'm not a PowerPoint wizard that can jump around, I actually chose red. Sorry. We're already, but so let's suppose you had chosen red so that PowerPoint will work. Instead of, if I had actual cards, I would put down 5 cards that are all black. But the PowerPoint cards are all red. And then what I would let you do is pick one of those cards and point to it. So 5 cards, which one do you want?
The middle one.
The middle one, okay. What I would do is start revealing the other cards. And PowerPoint doesn't do what you did. So PowerPoint, I did it differently. So I'll reveal the other cards, but the other cards would include the card that you did because PowerPoint-wise, I said, I assume that you picked the 4th card. Actually, it turns out that people very often do pick the 4th card in this. But anyway, let's assume that you had picked the fourth card, and I turn over all the other cards. At this point, if we had done this, then you would have reason to believe that the remaining card, whichever one it is, since I revealed all the others, the remaining card matches the selection that you made. So it's a little hard to think about it, because you said third card and I did fourth card or whatever, but assume that this is just a fictional representation. And what I had done is I put 5 cards in front of you, and you pointed to the third card, and I turned over the 4 other cards and showed that they were all black. And then, even though that last card never got turned over, you're not certain that that's also black, but you have good reason to believe that, right? If I were trying to cheat you, I would have had to guess in advance which card you were going to point to and make that one red and all the other ones black to try to fool you. And my chance of doing that, kind of 1 in 5, at best. So it would be hard for me. If I were to try to do that, there would be a good chance that I would be revealed. Now, this is not even actually what we would do. In voting, what we do is do this 1 card at a time. And the process is a lot easier. But it's easier to see how this works in this case. And the key thing here is that this 1 card that remains face down, you have reason to believe matches your selection, even though you haven't seen this card. Let's say it's a black card, even though it says red. You wouldn't know whether it's clubs or spades, even though you have reason to think it's black. You wouldn't know the rank. You don't know anything about it, except it probably is a black card because the other 4 that got turned over were all black. And I didn't know. I'm the voting machine. I didn't know which card you were going to point to. So you have reason to believe that this is what you want. We could have you sign your name to the back of this card and put it back, mix it up with other cards and shuffle them and turn them over later and count them. But you can't convince anybody else because once you walk away, you said, well, when I was there, I looked at the other cards. They were all right, so this one is probably right. And the way we would actually do this in practice would be you cast a vote, you say, what do you want? The machine gives you a vote, and then you say, do you want to keep it, or do you want to disclose it and try another one? And most people will keep it. That's fine. But people have an opportunity to disclose a vote and change it and to check the system that way. But in this case, you've never seen what the card is, but you have good reason to believe that it matches your selections, or in this case, my selections, which don't match your selections. Sorry, didn't work out. Most people choose red for some reason. I don't know why. Anyway, you have this non-transferable belief, so that even though you have reason to believe this card has a certain color, you don't have any way of showing it to somebody else. So we would do this in practice with encryption, of course. So what you have are many different encryptions of a selection. And let the voter select one or select whether or not to keep the one that was given and see that it matches what it's supposed to. But there are a few things that you'll notice about this encryption right away. It has to be randomized, of course, because you don't want it to be that every encryption of atoms looks the same as every other encryption of atoms. Then it can say, OK, we go through all this process. Here's a vote for atoms. Well, that one over there looks exactly the same. I wonder who that's for. So every encryption of the same thing should be its own unique encryption. So the ballot encryptor, an encryption device that a voter is using, should take a ballot, a choice, a random value, and use that to produce the ballot. So if the selection is atoms, then there's a random number that is chosen by the device, not by people, because people are terrible at choosing random numbers. And the person would then know the random number and be able to compromise things. So the device chooses a random number, puts that together with a ballot, and creates an encrypted ballot, creates an encrypted vote. Now, if the ballot stays the same, if the selection stays the same, but the random value changes, the encrypted ballot changes. So there are many different encryptions that are all votes for atoms here, and they don't all look the same. The decryption we want to be able to verify, because you want to be able to decrypt something in a way that will show that this really is the correct decryption. It's not good enough to just say, yeah, I decrypted that and I got what it was supposed to, I promise. You really want to be able to convince people. And the way to do that is, if we go back to this, then revealing the random value proves that the decryption is correct on anything that you do decrypt. Because now somebody who's trying to check the decryption is really just repeating the encryption, coming over here, saying, OK, if I take atoms and I take this random value and I encrypt it myself, because the encryption function is public, I can check and see if it matches what it's supposed to. And if it matches what it's supposed to, I say, OK, I guess that really does decrypt properly to atoms. So the way one of these things would look is you have a bunch of encryptions, and for anything that is to be opened, you reveal the random data. You reveal that. That serves as a key to allow anybody to check that the encryptions are all correct. Now, of course, people really don't have to do this kind of encryption. And I'm going to sort of skip through a bunch of ways of implementing this. I'm not going to. I'd love to talk more about this. I can talk about it individually later, but I see the clock is running, so my time is limited. One trick is something called a pret-a-voter ballot, which people mark and then throw away this, and the ballot is now just looks like this. But this code down here is an encryption of the choices that the voter made. And you can actually challenge as many ballots as you want and check through the process. So you can challenge ballots ahead of the election, during the election, after the election. Everything works. Okay? There's another way of doing this called scantegrity. The trick here is something where invisible ink is used to pre-fill all of the choices. And there's a code under the invisible ink. Voters seem to really like this, and this has been used in real elections, where they're given an invisible ink revealing pen, they swipe over their choices, and this means that they can sort of fill out a bubble sheet, not in the way we're always accustomed to, like, oh, I missed a little bit here, oh, I went a little over the edge there. You just swipe over it, and it fills in the bubble perfectly. And it reveals a code that you can use to check later on if you want to. And the code is, of course, different in every ballot. So I'm not going to go into that. Another trick is really what we did with the cards. And that's voters can use any device to make their selections, and then they get a choice. So voters make their selections on, say, a nice touchscreen device or filling out a bubble sheet or whatever. And after they're done, they get an encryption of their vote. Maybe a receipt that looks like a UPS tracking code or something like that. They get effectively an encryption of their vote. And they get a choice at the end of, OK, you've got your receipt. Now, do you want to cast this vote? Or now this is what your vote looks like. Do you want to spoil it and start over again? Maybe you spoil it by saying, wait a minute, that's not who I really wanted to vote for. Maybe I'll change it. Or maybe you spoil it because you know about this challenge thing that we did over here, and you particularly want to challenge a vote. Okay? So your choice is cast, which is effectively drop it in the ballot box, walk away. This is what 99% of voters will do. That's fine. Or you spoil it, which means you say, I want this ballot opened. And the ballot that's opened will show what it really is. Opening it gives that random data that allows you to check what it is. Now, voters don't need to do the decryption themselves. Like I said earlier, people aren't good at encrypting. I don't want people decrypting either, and they don't have to. A public record of an election, a manifest, would include all the ballots that are cast and all the ballots that are spoiled. And diligent voters really don't have to do anything more than check that things look the way they expected them to look. So an election record might look like this, where I've got all the cast ballots and the mathematical proof and all the spoiled ballots. And there's a key next to all the spoiled ballots. Each one of them has its random value, which can be used to check that the encryption is correct. So if I'm a diligent voter, a really super diligent voter, most voters aren't going to bother with this, and that's OK. But a super diligent voter might say, I'm going to spoil a ballot. And I'm going to go home, and I'm going to check the election record and see that spoiled ballot. Yep, that's there. And did it open to what it was supposed to, what I was expecting? Did it open to Adams if I was expecting Adams? Or did it open to Jefferson if I was expecting Jefferson? And I look there and I say, good. So who's doing the decryption? Who's checking this? Well, anybody can write an election app which goes through the election record and checks that all these decryptions are correct and that the mathematical proof over here is correct. The mathematical proof is just multiplying the ballots together and making sure that that's decrypted properly. So there's not much to that either. So just to give a quick sense, Rice University first class in programming a few years ago was given an exercise of write election verifiers, writing these little apps. And 2-week project, and most of the students were able to do it. You know, it's not that hard. So you can imagine that these election verifiers would be all over the place. You could write your own if you wanted to. You're all good students. You could do this. But your grandfather, who's not so good at this, might download an app, do it, use somebody else's app, or not bother. So I want to say quickly, even if there's very little challenging, very little spoilage, you get very high assurance. Just as an example, in a large election, 100 voters, a small election too, but if 100 votes are checked, 100 challenges are made across an entire election, then you still have, that's enough to have confidence that things are within 1%. I'm getting to the end, I promise. I know we're almost at 5 o'clock. We're using asymmetric encryption, so the devices that are doing this encryption don't have to be able to decrypt. They just have to have encryption keys. There's no real security issue there. Everything there is public. You've got the election record, which anybody can check. So I'm going to skip through all the checking that's done, but it's really just checking that the multiplication down here is done properly, and that also the tally is decrypted properly. So you check multiplications, you check the decryptions are proper. That's all there is to it. I'm going to skip through star vote, which is a system that I helped build that does this, and what the voter experience is. It's not that hard, but it's important to realize voters can take the receipts that they get when they vote. They vote, they get a receipt, which looks like a UPS tracking code, which really is just an encryption. And they can check it on a public website, or they can do what most voters will do with their receipts, is throw it away, no problem. Voters don't have to check. They can actually write these election verifiers, or run election verifiers from other sources, or just believe their favorite media outlet when they say, we checked, it's OK. Or do what most voters will do is say, yeah, I heard the results. I don't care anymore. Good, I'm done. OK? That's all right. I'll say a little bit about deployments. I've got like 2 quick slides left. There's Helios voting, which is an internet version of this. You can go and set up your own end-to-end verifiable election on Helios and run it with your friends, or for student body elections. And Helios has been used for a lot of student body elections, a lot of professional societies. The president of a university in Belgium, not the student body president, the actual president of the university, was elected with Helios in one deployment. Scantegrity is the one with invisible ink. That was used in a couple of real elections in Tacoma Park, Maryland. It's a suburb of DC. Star vote is something that was designed for Austin, Texas, but that's enough. OK. I'll say quickly, there's been an issue between security experts saying we need paper to get good verifiability, and accessibility advocates saying paper is not very good for blind voters, for instance. It's not very good for voters with motor skill needs. And there was a compromise a few years ago that said, you know what? End-to-end verifiability can solve this, so elections to be compliant with new Election Assistance Commission guidelines that are coming out hopefully this year, but the draft says they must be paper-based or end-to-end verifiable. Note, systems can be both. Star vote was both. We can have both. That's the best of both worlds. Should we allow internet voting? A lot of places saying we should do internet voting. There's a big push towards it. Well, here's a report I was a part of 3 years ago. The US Vote Foundation issued a report saying that if you do internet voting, it's got to be end-to-end verifiable. It's just the only way of mitigating all the other concerns about internet voting. But no internet voting system at all should be used until we get more experience with end-to-end verifiability in real simple poll site voting. And then when we get good at that, maybe we can then talk about internet. For today, don't do internet voting at all, especially not with blockchains, please. A lot of people want to use blockchains. No, it's a terrible, terrible idea. In the report, we devote a couple pages to saying, blockchain voting, no, don't do it. Don't do it. OK, that's the end. Sorry I ran over. Thank you. OK, any questions? Or do you want to ask for questions? I'm sorry.
I just wanted to announce that if people wanted to leave.
Yeah, yeah, OK. So if people want to leave, sorry, please, that door is friendlier to other people.